Okay, we are ready to go. So what we're going to do today is we are going to finish up our look at chapter 4 by taking a little deep dive into the normal curve. And then we're going to introduce chapter 5 and start up on that. And that is where we are going to make the shift from collecting tools to actually, for the inferential statistics, to actually doing inferential statistics. That all begins in chapter 5. So what we're going to do now is we're going to finish up our look at chapter 4. And again, these are the sort of final tools that we need, the final things that we need, skills that we need to develop in order to be able to do the really cool stuff that statistics allows us to do in psychology, in order to be able to do the hypothesis testing that opens psychology up from the sample to the world. And again, we've been working on all of our skills, and today is going to be the culmination of all that, where we finally graduate to being able to do or start hypothesis testing. And again, keep in mind, keep that goal in your mind, keep it in your vision, that what we're doing is we're opening up psychology for everyone. We are taking any work that we do with a sample of individuals, and we're using inferential statistics to intelligently go beyond those individuals. So instead of just limiting the impact of our psychology to a select few, we can impact the entire world as well. So what we're going to do to just finish this up is we're going to talk about samples and populations. We're going to touch on the distribution of sample means. We're going to take a look at the central limit theorem. And then, depending upon our time, we're going to begin our look at chapter 5. All right, so samples and populations. So up until now, we've distinguished between samples and populations a few times. So for example, in the calculation of variance, we had one formula for a sample, one formula for a population. But today we're going to be very explicit about what it is that we're trying to do with samples and populations, why that distinction is very important. And it all comes down to what samples are used for. Samples are used to estimate population parameters. And it is very rare that you're actually interested in your sample per se. Usually your sample that you're working on, that you're collecting data from, that's a gateway, that's a doorway to understand the population. So you use your sample mean, your capital M, to measure your, or to predict your population mean, to find out something about your population mean, and that's that Greek letter mu. So that's what a sample is for. You're always looking for a sample to tell you something about the population. But the challenge is that you use this to estimate the population. So we're dealing with a population where we don't know the mean and we don't know the standard deviation. And that is typical of most populations of interest. Usually we, in psychology, when we're studying a population, we don't know what the average score is for that population. We don't know what the standard deviation is for that population. There are a few populations where we do know that. So for example, in general, IQ tests have a mean of 100, have a standard deviation of 15. But as soon as you start looking at specialized populations, as soon as you start looking at the IQ tests of single mothers who did not finish high school, as soon as you drill down a little bit, we have no idea what the mean is. We have no idea what the standard deviation is. We're in a situation where we have no idea about this population. So we want to find out about this population. So what do? Well, we start taking people from the population as a sample. So we test this individual here, we test this individual here, this person over here, this person over here. So in this frequency distribution, we basically start pulling out individuals and we measure them from that population. And from those individuals, they form a sample. And that sample has a sample distribution, and that sample has a sample mean and a sample standard deviation, and those two are known. So you can find out about the mean of a sample, and you can find out about the standard deviation of a sample, and then we use this mean and this standard deviation to try to predict this population mean and that population standard deviation, and that's how we get to the population. We get it through the measuring of samples. So this is what occurs sometimes, and you can see here the mean that we have for the sample equals the mean that we have for the population. So in this case, our sample accurately predicts the population mean that we're looking for. So this is a great situation. We measure our sample, we found out the true population mean. However, the tricky part is that when we take a sample, because we don't know the population that it's coming from, we have no idea where in the population it's coming from. So those 5 people that we took to form our sample might come from the middle of the sample, like in this example, or they might come from the extreme edges of the sample. So we might find this person, and this person might come into our sample, and this person might be randomly selected for our sample, along with this individual and this individual. And now we have a sample of 5 individuals, and we calculate their sample mean, and we can do that, and calculate their sample standard deviation, and we can do that. But now we have massively underestimated the population mean, and importantly, we have no idea that we did that. So we have underestimated the population mean, but because we don't know what the population is, we don't know that we've underestimated it. So that's one scenario that could occur. And then we have the opposite scenario. So when we take our sample of 5 individuals, we might randomly select that individual there, or that individual there. And then this individual might be in our sample, and this person, and this person. And once again, super straightforward. We already have these skills. We can calculate the sample mean, we can calculate the sample standard deviation, but now we have massively overestimated the population mean. So now we're on the opposite end. We're on the overestimation side. And again, no idea that that's what we actually did, because again, we don't know what the sample is. So this is a challenge. Different samples from the same population are going to give us different sample means, and most sample means are not going to equal your population mean. Just by chance, they're going to be a little bit over, or they're going to be a little bit under. They might be a lot over, they might be a lot under, but it's very rare that you're going to choose, 5, or you're going to choose a sample of individuals where the sample mean is exactly the population mean, right? It's kind of like if you flip a coin 100 times, on average, you're going to get 50-50. But it's very rare that you flip a coin 100 times and you get exactly 50-50. So that's what's the scenario here. It's very rare that you're going to take a sample and get a sample mean that is exactly the same as your population mean. And that difference between your sample mean and your population mean, that's called sampling error. And that's just the distance between your sample mean and what you're trying to estimate, which is your population mean. All right, so what do we do with this? Well, what we do with this is we take advantage of the fact that different sample means have different probabilities with which they will occur. So that's a key point, key takeaway point for today. The idea that some sample means are more common, they have a higher occurrence, they have a higher probability, and other sample means have a much lower probability. So let's take a look at, I'll give you an example of this. Let's say that you and your friend sign up for an IQ Olympics, right? So you and your friend are going to compete in the IQ Olympics, and you are going to be randomly assigned to a team, all right? So out of everybody that signs up for these competitions, you are going to be randomly assigned to a team of individuals from that population of people in the world. All right, let's make it simple. Let's say everybody in the world is signed up for this game. It's an IQ game. You and your friend get randomly assigned. So you take a look at who's been assigned to your team. So we got 6 people on the team. You're one of them. Who are the other 5 people? And it just so happens that these 5 individuals are on your team, right? So we have ourselves a college student, recent college graduate. We have a PhD. We have somebody in the workforce for a number of years. We have another recent college graduate. And, their intelligence, their IQ scores are going to be, they're going to have a range of IQ scores for sure. But this team feels very believable, right? When you take a look at your team and you say, oh, what do you do? And they're like, oh, I'm still in university. You're like, oh, okay, that's very believable. And what do you do? Oh, I've been working, for an accounting firm for the last 30 years. Oh, okay, that's very believable. And what do you do? Oh, I just recently graduated. Oh, okay, well, congratulations, that's very believable. This is a very believable team. You wouldn't look at this team and be surprised, right? And that surprise, that lack of surprise, means that you intuitively understand that this is a highly probable team. This is a highly probable sample from the world. To get these 5 people from the world is a highly probable thing to occur. So that was your team. Now let's say that you then go to your friend, and your friend says, hey, well, how's your team? And he said, well, it's kind of what I expected. I would find, somebody that's still in school, somebody that just recently graduated. We got somebody with a lot of experience, kind of what I would have expected. What about your team? And then your friend says, well, let me tell you about my team. I walk in there, first person I see, Bill Gates. And you'd be like, whoa, what are the odds? Right? What are the odds that you would get somebody so extreme in an IQ Olympics? You would get somebody so extreme, that seems highly unlikely. But your friend pulled that one out randomly. And you said, all right, who's your next teammate? And they're like, well, you wouldn't believe this either, Neil deGrasse Tyson. And you're like, whoa, like what are the odds? Like the super what are the odds, right? Because now we got 2 of the most intelligent people on the planet. And you're like, all right, that really seems unlikely to have occurred. Who's your third player? And they're like, you're not going to believe this, Bill Nye, the science guy. Can you believe it? And you're like, no, I can't. Because now it's getting to the point where it seems so unlikely. And you might say, all right, well, you got 3, IQ killers in there. Who's your next contestant? And you're like, who's your next player? And they're like, well, it's Marilyn von Savant. And you're like, really, the highest recorded IQ ever just happens to be on your team. Who's your last player? And they're like, oh yeah, it's Ruth Lawrence. And you're like, oh, the Oxford graduate at 13 who got her PhD in mathematics at like 16, that one. So these are 5 of the top individuals in the world. And you can see that just intuitively, you would look at your friend and say, I can't believe your luck, right? That seems so improbable. Like your team, yeah, seems about right. Their team, 1 in a bajillion chance that you'll get those 5 people. So you can see that some teams are very high probability, other teams extremely rare. Specifically, teams that kind of come from the center and are spread throughout the population, highly probable. Teams that come from one side and extreme versions from one side, very, very, very improbable. And we can use that and we can measure that to give us a measure of where in our, how likely we are to have estimated our population mean correctly. So that's a challenge. We want to tell what the probability is of selecting a particular sample with particular characteristics from a population. We want to know what is the probability of getting a sample from the center of the population, what's the probability of getting a sample from the ends of a population, and somehow calculate those to know what our chances are of estimating our population correctly. So what we want to do is want to know the probability of getting a particular sample. And if you recall, when a statistician talks about probabilities, we're talking about proportions. And when we talk about proportions, we're talking about proportions of a distribution. All right, so any questions so far? All right, let's keep going with this. So, we want to know how likely is it to get a particular sample out of a population. And in order to do that, we need a proportion. We need a proportion of a distribution. So now we need a distribution. So what distribution are we going to use? And this is where we kind of go into levels upon levels. This is where we kind of go into that sort of like inception, dream within a dream kind of situation. Because now we're doing a distribution of distributions. We're doing a distribution of sample means. So a distribution of sample means is exactly what it says. It is a new frequency distribution that is made up of sample means. So it is a collection of sample means for every single possible random sample of a certain size. So you pick the size you want, every single sample of a particular size that you can get from a population. So what it literally comes down to is the idea that if we were doing our Olympics, if we were doing our mental Olympics, you would say, all right, I want to make a distribution of sample means. I'm going to do it with 5 individuals, right? So my size of my sample is 5, and let me take that first sample. So you go into the population of the world. This is why sometimes it's a little hard to wrap your mind around these things. You go around to the population of the world, you take 5 people, you measure their IQs, and let's say that you get an IQ, a mean IQ of 97, right? Sample number 1 has a mean IQ of 97. You throw them back into the world, you take a new random set of 5 people. That is sample number 2. You measure their IQs, you take the average. Sample 2 has an IQ of 105. You throw them back into the population. You take another sample. This is sample number 3. You measure their IQ. Let's say that sample number 3 has a pretty high IQ average, an average of 120. Throw them back. Take another 5 people. Sample number 4. Measure their IQ. Let's say that their IQ is 95. And you keep doing that, and doing that, and doing that. This is the part that's kind of hard to wrap your mind around. You keep doing that until every combination of 5 people in the world has had their IQs measured. So at some point, you're going to end up with sample 1,087,467,582. And you're going to measure their IQ, and it's going to be 101. And you're going to throw them back, and you're going to keep going until every single combination occurs. Once you have all of these means, once you have all of these scores, you can put them into a frequency distribution, and that is going to be your distribution of sample means. So these are all the sample means. You take them, you put them in a distribution of sample means. So each of these points here is another sample mean. Each of these points comes from a sample distribution. So this is a distribution of distributions. It's a distribution of sample means. All right, so keep that in mind because we're going 2 distributions deep for this. But let's give you another example that we can kind of see a little bit more clearly and kind of see what happens because the numbers are a little bit easier to handle, and that is dice rolls. So let's go back to dice rolls. And in the population of dice rolls, if you look at every single fair 6-sided dice that has ever been thrown in this world, and you were to count up all those throws and take the average of all those throws, you would find that the population mean for dice throws is 3.5, right? Because it goes from 1 to 6, so the average of those is 3.5, so they're all equally likely to come up. That's the average for the population. And if you took a look at the distribution of the population, and again, we're talking about fair dice, if you take a look at the distribution of the population, that's what it'll look like. It will have, on average, the same number of outcomes for a roll of 1, the same number for a roll of 2, the same number for a roll of 3, 4, 5, and 6, same proportion, same probability for all 6 outcomes. That's the population. So let's say now that you are taking samples from this population, and your sample is a single dice roll. So what you do is you take a dice and you throw it, and whatever comes up, you record that, and you calculate the mean. So basically, if a 5 pops up, you take 5, and then you divide it by 1, right? We take the sum of the scores. There's only 1, so it's 5. We divide by the number of scores. We divide by 1. So the average here would be 5. You throw it again. If it's a 3, the average for your sample is 3. You throw it again. If it's a 2, the average for your sample is 2. And you keep doing this for every single possible sample. As it turns out, there's 6 possible samples, right? 1, 2, 3, 4, 5, and 6. And if you calculate the mean of those sample means, okay, so again, we're diving down 2 levels. If you calculate the mean of the sample means, you'll see that the mean of the sample means is the same as your population mean. So that's very useful. That's why we use sample mean to estimate population mean, because on average, it's going to be a good estimator. It's going to be an unbiased estimator. And if you were to graph all of these scores from your single dice rolls, if you were to graph all of the means from your single dice rolls, in this case and in this case only, it would look like your population distribution. So this is your population distribution here. This is your distribution of sample means. There we go. And it only looks like your population for a sample of 1. And that is why psychologists do not like to use samples of 1. And that is why if you ever read case studies, which are samples of 1, it's like one individual, we're going to study this one individual, you will see that they do not do inferential statistics on case studies, because we can't, for reasons that will become apparent in just a little bit. All right, so this is the distribution of sample means for this case of 1, sample size of 1, and only for that case, your distribution of sample means looks exactly like your population distribution. So let's see what happens now when we increase our sample size. So now we're going to sample 2 dice rolls, right? We're going to take 2 dice and we're going to roll them. So if a 5 and a 5 comes up, we calculate the mean of that sample. So we add them up, it's 10, we divide by 2, 10 divided by 2 is 5. This sample has a mean of 5. So then we do that for every single possible sample. And we calculate them, so we roll a 3 and a 5. Take the average, it's an average of 4. We roll a 3 and a 2. Take the average is 2.5. And we do this over and over and over again until we get all 36 possible samples from this population. And if we calculate the mean of all of those samples, right, so we get the sample means, and now we calculate the mean of all the sample means, we'll find once again that the mean of all the sample means is 3.5. So once again, it predicts our population mean. And when we take all of these means and we graph them in a frequency distribution, something weird starts to happen, because the shape of our distribution of sample means starts to change. Right? So we lose the shape of our population. It no longer looks like our population looked. Now the distribution of sample means looks like this. So we've lost the population distribution shape. So we continue this and we go on to 3 dice rolls. So once again, we're rolling 3 dice now. Throw 3 dice, add up all 3 scores, divide by 3, that's your sample mean. Do it again, add up all 3 scores, divide by 3, that's your sample mean. You're going to do this for all 216 combinations of dice. And if you do that, and then you take the means of every single sample mean. So we have all the sample means, we take the mean of all those scores, we'll get a mean of 3.5, once again. So that doesn't change, and that's very nice. The center of your distribution of sample means is always the mean of your population, but now our distribution of sample means has changed again. So this is the distribution of sample means for 3 dice. This is for 2, this is for 3. And if we do this for 4, and we run this game again, and we calculate every single possible sample from rolling 4 dice, add up the scores, divide by 4, calculate the sample mean, do that for every combination of 4 dice, and then we have all those sample means, and we take the mean of all those sample means. Once again, mean is going to be 3.5. Mean is going to be the same as our population mean. And this, now we're going to see, this is for the distribution of sample means for 3 dice. That's what it looks like for 4 dice. And we're going to finish this analysis by going to 5 dice. So once again, we do the same scenario. Once again, we roll every possible combination of 5 dice, calculate the sample mean for every possible combination of 5 dice, and then we take all of those sample means and we calculate the mean of those sample means, and hopefully you guessed the answer. The mean of that is going to be 3.5. And this distribution of sample means for 5 dice changes to that. And as you can see, we are getting very, very close to a normal distribution. we are getting very close to that distribution that you find in Appendix A1, and that is the reason why we use samples. Because when you use samples, you get closer and closer. The larger your sample, you get closer and closer to a distribution of sample means that is normally distributed, which means that you can do stats on it and be confident that the distribution that you're analyzing is a normal distribution. So that distribution of sample means is also called a sampling distribution. If you see that term, you'll know it's the same thing. We're going to use distribution of sample means, but just so that you know, that's what that sampling distribution is. All right. Any questions so far? Okay, so what we've been doing so far in this kind of analysis is an incredibly artificial situation, because in the real world, you can't do what we just did. You can't discover a distribution of sample means by measuring 5 people, recording their mean, and then getting a new 5 people and recording their mean, and then getting a new 5 people and recording their mean, and doing that billions of times in order to generate your distribution of sample means. Usually in psychology, usually in any sort of scientific experiment, you only have the one sample. You only have those 20 people that knocked on your lab door and decided to sign up for your experiment. So we usually only have one sample. How is it that we figure out this distribution of sample means? This distribution that's going to tell us how likely our sample is to have come from a particular population. So the answer to that is a little bit of math magic that is known as the central limit theorem. So the central limit theorem is what allows us to calculate our distribution of sample means from a single sample. So we're going to start off a little bit with the easily understood situation, and we're going to start off with the idea that we know what the population is. So when we introduce hypothesis testing, it's easier to kind of get a handle on some of these concepts if we start with a known population, and then as we go along, we're going to introduce more realistic situations where we don't know the population. So don't get thrown off at the beginning by us saying, well, you know, let's assume that we know the population. That's just to introduce the concepts. So let's take a look at the central limit theorem. So for any population where we know the mean and we know the standard deviation, so we already are dealing with this artificial situation. However, for any population with a mean of mu and a standard deviation of sigma, the distribution of sample means, that distribution that we're looking to attain so that we can deal with a normal curve, the distribution of sample means from a sample size of n, so it's always with a specific sample size, we'll have a mean of mu and a standard deviation of sigma divided by your square root of the size of your sample. So it's a mean that's equal to your population mean and a standard deviation that's equal to your population standard deviation divided by the square root of the size of your sample. And then lastly, it's going to approach a normal distribution as your size of your sample approaches infinity. So the bigger the size of your sample, the more normal your distribution of sample means will be. So importantly, the bolded parts here are the important parts of the central limit theorem. The first one here is that it's for any population. And that opens up psychology to anybody. There's literally no population that is off limits in psychology. There's no population that is beyond the study of psychology. You can go as weird and wonderful in your population as you want. You can still use the tools that we use here to understand that population. So it doesn't matter what your interest is, it doesn't matter who you're trying to help, there's no population that is off limits, and that comes from the central limit theorem. The second one here tells you what that distribution of sample means is going to look like. It's going to have a mean that's equal to your population mean, and it's going to have a standard deviation that's equal to your population standard deviation divided by the square root of the size of your sample. Don't worry about why it's the square root. Just know that it is the square root of the size of your sample. But that's how we determine the mean and the standard deviation of your distribution of sample means. And then the last thing we need is the shape of the distribution of sample means. And it says that the bigger your sample, the closer and closer the shape of your distribution of sample means will be to a normal curve. And that last part is what really opens up our ability to help a population, to help anybody, because once we're dealing with a normal curve, then we know what the distribution is. And once we're dealing with a normal curve, then we can use all those skills that we were working on, all those skills where we went to Appendix A1, and we can figure out things about how likely our samples are. We can figure out things about our population by not dealing with the population distribution, because we have no idea what that might look like, but we do know for a fact, because of the central limit theorem, that our sample distribution, our distribution of sample means, looks like a normal curve. And that's the key. That's why we need this move. That's why we use samples. So to just kind of give you a side-by-side comparison of this, once again, we'll start off with an example that we already saw. If this is your population distribution, right? This is your population distribution. Most times, this is completely unknown. So you don't know what this looks like, all right? This is just for illustration purposes. You have no idea what this looks like. But you do know about your distribution of sample means. So if you choose to use only one person in your sample, then your distribution of sample means is going to look exactly like your population distribution. And you're going to have no idea what your distribution of sample means looks like, because you don't know what your population looks like. So we're still in the dark. We still can't do anything with our data. But as soon as you start taking more than one individual, as soon as your sample starts growing, this is what a sample distribution of sample means from this population looks like when you have a sample size of 2. This is a distribution of sample means for a sample size of 3, sample size of 4, and sample size of 5. Importantly, still from this population. But now that we have a sample size of 5, that is looking very much like a normal curve. And now we can start accessing that appendix. Now we can start using the skills that we've developed. Now we've opened up the ability to do intelligent, meaningful work using our statistics skills. So that's when you're dealing with a population distribution that looks like that. What about a population distribution that looks like this? What if you're dealing with dice where somebody colored in 4 more pips on the side that only had 1, right? So maybe somebody's running a shady gambling establishment, and they have a dice that has 2 5s on its side. What about that population distribution? Well, once again, if you're using a sample size of 1, your distribution of sample means will look exactly like your population distribution, and you'll have no idea what that shape is. Sample size of 2 looks like that. Sample size of 3 looks like that. Sample size of 4 looks like that. Sample size of 5 looks like that. And you can see that already, just with 5 individuals in our sample, our distribution of sample means is starting to look very much like a normal curve. So imagine how much more like a normal curve is going to look after a sample of 10, 15, 20, which is usually like the minimum that people would use for a psychology experiment. And again, this works for any population. So if we have a population that looks like this, sample size of 1 gives you a distribution of sample means that looks like this. Not useful, can't do stats on it. Sample size of 2, sample size of 3, distribution of sample means for a sample size of 4, and there we have a sample size of 5, and you can already see, even with something as bizarre as this, that bell-shaped curve is coming in, that normal distribution is coming in, and that's what allows us to do psychology. So this central limit theorem, this is the gateway through which we get from a sample to a population. This is the gateway that we get through helping just a few people to helping the world, and it boils down to the fact that, number 1, this works for any population. Number 2, your distribution of sample means will have the same mean as your population, and it'll have a standard deviation that's squeezed in a little bit. It's the standard deviation of the population divided by the square root of the size of your sample. But very importantly, it approaches a normal distribution the bigger your sample is. So as your sample approaches infinity, it approaches a normal distribution. And this is why you can do psychology work on any population. So you can do psychology work on single fathers who have recently immigrated to the United States. If that's your population of interest, barely anybody has population data on those individuals, but you could do a study, take a look at a sample, and know that your distribution of comparison means is normally distributed regardless of what you're measuring. Think about populations that didn't even exist, decades ago, right? Think about people in gay marriages, right? Before legalization, there were no gay marriages. This population literally came into existence very, very recently. How can you do research on a population that only came into existence? We have no idea what the distribution is. Central limit theorem, distribution of sample means. Take a sample of gay married couples, measure them, and you know that the distribution that sample came from is a normally distributed distribution of sample means. And you can do this for any population. So when I was doing my senior seminar for the first time, this student came up to me and she said, "Can I do my work on this new group that I found?" And I was like, yeah, my first answer was yes, you can, because I knew the central limit theorem. What was her group? It was connected Bohemians. Anybody here have any idea who connected Bohemians are? Exactly, neither did I. So as it turns out, there is it's called the Claridus prism. It's a set of demographic segments that marketers use and other corporations will use to try to understand who their demographics are. And it is a list of literally I think 50 or something different types of people that you can find here in the United States. So we have things like home sweet home, widely scattered across the nation's suburbs and second cities. These residents tend to be younger, families live in mid-sized homes. We have big sky families scattered in placid towns across America. Heartland, they are middle-aged rural families who have high school educations and blue-collar jobs. We got bright lights, Lil City, college-educated younger couples who settled in the nation's satellite cities and suburbs. Despite living further out from the urban downstairs, they still like to do something. But we have connected Bohemians. So connected Bohemian, mix of young singles, couples, and families ranging from students to professionals, all having one thing in common, being tech-savvy. They're always early adapters of the latest and greatest thing. I don't know if anybody's ever done a psychology on connected Bohemians before she did a study on connected Bohemians, but I knew immediately that she could do a study on connected Bohemians because the central limit theorem works for any population, right? It's not just select populations. It's not any population except connected Bohemians. It's any population. And once you choose your population, as soon as you take a sample from it, you know your distribution of sample means is going to have that mean of mu and that standard deviation of sigma divided by the square root of n. Same mean as your population, standard deviation equal to the standard deviation of your population divided by the square root of n. But importantly, you know that the distribution of sample means is going to be normally distributed. And that means that you can do statistics on it. You can go to Appendix 1. You know that you can access this distribution. All right, so that central limit theorem allows us to figure out the distribution of sample means. It allows us to use z-scores and the unit normal distribution table. So it allows us, like I said, to go to that appendix and make intelligent and useful use of that appendix. And this is, again, this is the gateway to doing what we're just going to see in a moment, which is the ability to go from a sample to helping an entire population. All right, any questions on that? All right. So just a sort of public service announcement right now. Now that we've introduced the distribution of sample means, we are going to be continually dealing with 3 distinct distributions. And it is very important that when you're doing your statistical work, you are very intentional and very conscious about which distribution you're currently working with. Because previously it was fine, we could just say distribution and we'd be like, oh, probably population distribution. Now, however, we're dealing with 3 of them, so just make sure that you always have it in your mind, what am I talking about here? Because we have our population distribution. This is the distribution of everybody that we're interested in. This is the distribution of everybody that fits our particular category. And then we have our sample distributions, and these are the distributions of samples that we take from that population. So they're a subset of the population, and they have their own distribution. And then now we have a third one that is the distribution of sample means, and that is the distribution that is formed by taking all of these sample means and collecting them into their own distribution. And it's tied directly to the population distribution by the central limit theorem. So we got 3 distributions floating around in the air right now. They're all kind of named the same, right? Distribution of sample means, sample distribution, population distribution. So as you're going forward, make sure that you're very intentional, slow down, think about this slide right here, make sure that you're very solid on which distribution you're talking about, because it's easy to make a mistake if you're supposed to be dealing with the distribution of sample means, but you substitute in the population distribution instead. That leads to errors, and we want to make sure that we don't do any of that. All right, so any questions on this central limit theorem, what we've just covered? No? All right. So that wraps up chapter 4. What we're going to do right now is we're going to introduce chapter 5, the introduction to hypothesis testing. And the reason that I'm going to do this, we're probably not going to have time to cover the whole thing, but more so than anything in this course that you're going to encounter, hypothesis testing has a very variable number of times that students need to see it before it makes sense. So this is one of those concepts where, unlike the mean, right, when we went through the mean, when we went through the median, I think just about everybody got that on the first try. After we went through it in class, I think just about everybody was on board and said, that makes a lot of sense. For hypothesis testing, there's going to be some of you where after today or tomorrow's class, you'll be like, oh yeah, that makes sense. There's going to be others of you where it takes 2 times to make sense, 3 times to make sense, 5 times to make sense. So that's just something that's going to happen. That's just the way that, you know, our minds work. However, just so that to put you at ease, there is a 5-step procedure for hypothesis testing where even if you don't understand what you're doing, you can still do what you're doing. So it's kind of like turning the lights on in a room, right? You might be an electrician and understand electricity and currents and connections and wires and how a switch operates, and you will know the fundamental principles of it, and you'll know about what goes on when you turn on the light switch. And that's great. That's where we want to get to eventually. However, most of you probably just know how to turn on a light switch. You just know that, well, if I go to the wall and I flick it up, it'll turn the lights on, and if I flick it down, it'll turn the lights off. And that is good enough until you get to that deeper understanding. So we're going to go through hypothesis testing, and I guarantee you it's happened to every student that's ever been in my course. At some point, it's going to click. And at some point, you're going to be like, oh, I get it now. That makes sense. Oh, of course, that's what we're doing. However, up until that point, even if you don't get there immediately, you're going to have a 5-step procedure where you're going to say to yourself, I might not know what I'm doing exactly, but I know I can do this, 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 and this, and I'll make the right decision. I'll get to the right answer. And that is where we want to get, at least in this course. All right, so hypothesis testing. It's all coming together now. You're going to see that we're going to use everything that we've used up until this point. We're going to use population means. We're going to use sample means. We're going to use standard deviations. We're going to be calculating z-scores. We're going to be doing all of the stuff that you've been practicing. We're going to put it all together into one huge kind of procedure. And the more practice you put in and the more automatic these things are, the more you're going to be able to concentrate on each of those individual pieces. So this is the cool part we finally hear. This is the part where we finally get to take a look at data and do real psychology, inferential work. And for those of you that have the capstone courses on the horizon, if you do the advanced lab, this is where we begin the skills that you might actually use in your advanced lab. So if you collect data for your research project, the skills that we're going to take a look at and the tests that we're going to take a look at for the remainder of the semester, you might actually say, oh, I need to use that test for my advanced lab. So it all begins here, right now with chapter 5, with our first kind of hypothesis testing procedure. All right, so let's set this up with an example. So let's say that you graduate from IUSB and you become an educational psychologist, right? So you dedicate yourself to the study of how do you educate people, you know, with the best possible outcomes. And let's say that a school calls you up one day and asks you to come in and assess their children because they're kind of worried about the level of self-esteem in their students. They've started to notice that maybe there's a self-esteem issue with their students. And you go in there and you take a look at their curriculum and you realize that they have a very kind of typical standard physical education program, right? Gym class is basically your standard sort of practice drills and push-ups and sit-ups and things like that. And you, because of your training, have come up with a new program that you call a games program. And this one will still give these children the physical education that they need, but it's in a games sort of scenario or framework. And what you want to know is this going to help the self-esteem of these children? So you've developed this game program to increase the self-esteem of children, and you want to know, is it going to work for children? And importantly, you're not interested in just these students. You want to know, is it going to work in general for the population of students? So what we're going to see here is a scenario where we know the self-esteem of the population of students in general, and we're going to see if the self-esteem of the students that go through your games program is actually higher than the self-esteem of the general population. So that's where we're going to begin our hypothesis testing journey. All right, so the outline, we're going to start off with the core logic of hypothesis testing. This is going to be the peek behind the curtains, right? This is going to be the electrician talking to you about how electricity works and how wiring works. And then we're going to take a look at the hypothesis testing process, and this is going to be your procedure for doing this. This is going to be basically instructions on how to use a light switch. You flick it up, you flick it down, depending upon whether you want the lights on or off, and that's what we're going to do, and we'll see how far we get in the remainder of the time that we have. All right, hypothesis testing. So what hypothesis testing is? It's a systematic procedure. It is a step-by-step procedure that you can apply to any situation where you want to know if the results of a research study on a sample applies to a population. So this is where you take a sample from your population, you study the sample, you measure the sample, you find out something about that particular sample, and then using hypothesis testing, you intelligently are able to generalize that or not generalize it, so it goes both ways. It makes the decision about whether you generalize your results or don't generalize your results to the entire population. So it is what allows us to, again, intelligently say, based on my sample, my procedure will work for the population, or based on my sample, my procedure will not work for the population. It lets us make that decision. Importantly though, again, we have that theme, we're measuring a sample, but we are interested in the population. That's the goal, that's the impact that we want to have. All right, so researchers always want to draw conclusions about a particular population. So for example, for our self-esteem example at the top of the this chapter here, We're not interested just in the 16 individuals in the class. We want to know about the population of school children. We want to know about students in general. So these conclusions are going to be based on studying a sample. And just so that you have a heads up, your book starts off with a sample of 1. So a sample of 1 is the wrong way to do it, but it's the simpler way to do it. And I just have a hard time teaching the wrong way and then correcting it later. I think that's not a great idea. So we're going to learn it the right way right off the bat. But just so that you know, your book is going to start with a population of 1. And it's going to kind of set you up for, I'll put a red flag up when you need it. But for right now, just know that your homework is going to say, oh, you take one sample, you take one person, you take one thing. And that's going to be the basis of what they do, but we're going to learn it the correct way in class here. All right, so here's the logic of hypothesis testing. So the first thing we're going to do is we're starting off with a known population. We're going to start off with this incredibly rare case where we know the mean of a population, we know the standard deviation of a population. We're going to start off with this rare case because it just makes the sort of education of this easier. This is the easy example. If you can just accept that we know the population, the rest of it makes it a whole lot easier. We're going to get to more realistic scenarios though once we get the core logic down a little bit better. So we start off with a known population. We know the mean, we know the standard deviation. And what we want to know is that if we take a treatment and we treat that entire population, will that population be transformed into a new population, a treated population, right? So if these people are depressed, if this is the population of depressed individuals, if we treat them, will they then change into a population of not depressed individuals? If this is a population of students with low self-esteem and we treat them, will they transform into a population of students with high self-esteem? Now, even if we could do this, logistically, it would cost amazing amounts of money. It would take a lot of time to do this. Ethically, this would probably be a super bad idea because if your treatment is harmful, you've harmed an entire population, right? So we don't want to take a chance on an entire population, even if we could, and we usually can't. So what do? We take a sample from our known population, and we treat that sample, and then what we do is we end up with our treated sample, and the decision we want to make is, does our treated sample, has it changed enough that it now must belong to a new population, or does it still belong to the old population? So has this changed enough so that it now belongs to this new treated population, or does our treatment does nothing, and our sample still belongs to our known population? So one last thing that we're going to do, one last assumption we're going to make, and again, this is just because the math is a lot easier. This assumption was for those poor grad students locked in their ivory tower doing statistics by hand. And as it turns out, if you're dealing with a treated population where we don't know what the mean is, and we don't know what the standard deviation is because we don't know what our treatment does, right? If we're dealing with an unknown treated population, the math becomes massively easier if you assume that the standard deviation of your treated population is the same as your known population. So that's just a fancy way of saying that all our treatment does is move everybody to a new position. It doesn't squeeze or it doesn't stretch or squeeze the distribution. It just takes everybody and moves them all the same amount to a new position. All right, so that's what we want to do. We basically take a sample from our known population, treat it, end up with a sample from, end up with this new treated sample. We measure this sample here, and then we decide, is this sample different enough that it belongs to the treated population, in which case we say our treatment did something, or is it not different enough so that it must still belong to the untreated population, i.e. our treatment did nothing. So that's the core logic of hypothesis testing. We're going to end today with an intro to the hypothesis testing procedure, and we'll take a look at the null hypothesis specifically and the research hypothesis, because that's the gateway, that's the door in to the hypothesis testing procedure. That's step number one. So step number one, you want to restate the question as a research hypothesis and a null hypothesis about the population. Never about the sample. We are not interested in the sample. We are interested in the population. So everything about the hypothesis testing procedure is going to be about finding out things about the population. So the hypothesis that we want, the does this work for, that we're looking for, is never does this work for the sample. It's always does this work for the population. So we're going to restate the question we have as a research hypothesis and a null hypothesis about the population. We are going to determine the characteristics of the comparison distribution. The comparison distribution is going to be our distribution of sample means. We're going to determine the cutoff sample scores on the comparison distribution at which the null hypothesis should be rejected. We're going to draw lines in the sand on our distribution, and if our sample mean crosses those lines, we're going to make one decision. If our sample mean does not cross those lines, we're going to make another decision. And step 4 is where we find out where our sample is. Has it crossed the line? Has it not crossed the line? And then finally, step 5, we decide what to do based on whether our sample has crossed the lines we drew in step 3, or has it not crossed the lines we drew in step 3. So these are the steps. And again, if you're going to see that these are pretty straightforward, they are very well-defined steps. And even if you don't understand what you're doing in terms of a hypothesis test, you do these correctly, you can get to step 5, you'll make the right decision, and you might not know why it's the right decision, just like we don't know why a light switch works, but we can still turn on the lights, and that's what we're looking for in hypothesis testing. All right, so we're going to end with step 1, but we'll introduce this idea. So step 1, you want to restate your question that you're interested in as a research hypothesis and a null hypothesis about the population. So we might, in general, we might say, is there a difference between the treated population and the untreated population? That's what we want to know. Does our treatment make a difference? Has our treatment changed the population? That's what we're looking for. In this case, we have 2 possibilities. One possibility is that our treatment did change our population. The other possibility is that our treatment did not change the population. Those are your research and your null hypotheses, respectively. So the research hypothesis is that your treatment does have an effect, and we write that out as the mean of your treated population does not equal the mean of your original population. So the mean of your treated population does not equal the mean of your untreated population. So let's take a quick look at why this means that your treatment has an effect. So let's say that I develop an IQ pill. All right, I have a pill, miracle IQ pill, and I'm telling you, if you take it, your IQ will change. It'll have an effect on your IQ. So let's say that I'm able to test this out on the entire population. And the original population, our untreated population, has a mean of 100, right? That's the standard population for, that's the standard mean for an IQ. And I give the entire population an IQ pill, and their IQ goes up to 140. The original population mean, untreated population mean, does not equal the new population mean, right? If I have a pill that takes your IQ to 140, yeah, that treatment has an effect. It has increased your IQ. And we know this because the original mean, untreated mean, does not equal the new treated mean. So we have this one being larger than this one, i.e. not equal. Now it's not equal because there's 2 ways you can have an effect, right? There's 2 ways that your treatment can have an effect. Because if I was a horrible, horrible scientist and I had no idea what I was doing, I could give the entire population this IQ pill, and it could take their IQ down to an average of 80. Now notice, it still had an effect. It had a horribly wrong effect, right? We've done a disastrous thing here, but it still had an effect. And we know that because the mean of the original population does not equal the mean of the treated population. In this case, it's less, And that's why this one is specifically not equal, because it covers cases where the treatment makes things better, and it covers cases where the treatment makes things worse. In short form, it covers things where the treatment does something, right? The treatment has had an effect, it's done something. That's the definition of does something. Your treated mean does not equal your untreated population mean. So that's the research hypothesis. The other hypothesis is your null hypothesis. Your null hypothesis is that the treatment has no effect, right? It has a null effect. If it got zero effect, your treatment does nothing. And we write this out as the mean of your treated population equals the mean of your untreated population. So again, if I went into, let's say that I went to the Nobel Prize Committee, and they said, tell us about your IQ pill. If I go into the Nobel Prize Committee and I say, yes, my IQ pill takes you from 100 to 140, they would say, Dr. Yurichevich, well, how do you want your Nobel Prize money sent to you? You want it wired directly to a Swiss bank account? You want it in cash? How would you like it? They would say, wow, what an effect. If I went in there and they said, tell us about your IQ pill, and I said, wait, just wait until you hear this. You start off with an IQ of 100, you take my pill, and you end up with an IQ of 100. They would say, your pill does nothing. It's useless, get out of my office, and please refund us the plane ticket money that we gave you to get here. All right. If your treated mean is the same as your untreated mean, you've done nothing. You've changed nothing. Your treatment has no effect. That's what's captured here. So if your treated mean is the same as your untreated mean, you've done nothing, you've changed nothing. That's the null hypothesis. So that is the beginning stage of the research hypothesis testing procedure. It all starts with the restatement of your question, and then the rest of the steps 2 through 5, is where we go through the procedure to decide, are we going to accept the research hypothesis that our treatment did something, or are we going to accept the null hypothesis that our treatment does nothing? And that's hypothesis testing in a nutshell. So that is what I wanted to cover for today. We got about 5 minutes left. So if anybody has any questions on anything for the course, let me know. Other than that, feel free to call it an early day. And let this kind of hypothesis testing sink in. And also take comfort in the fact that even if you don't know what's going on behind the scenes, the 5 steps are very straightforward. They're 5 well-defined steps. So I have had students who had no idea about the core logic of hypothesis testing, but were able to do hypothesis testing perfectly because they understood the 5 steps. Eventually, they got the understanding, but until you get there, take comfort in the fact that you're covered, you got those 5 steps. Other than that, we're done for today.